Got a little summary table of what we did yesterday up on the board here. Three equations, two of which were not new, one of which was brand new yesterday. First two equations we've learned about a week ago. Yesterday we drew a little Venn diagram and circled those two equations in red. The reason that we circled those together is because those two equations are both valid when we have a non-uniform field. And what's a non-uniform field look like? Well, when you got a field that looks like this. Okay, maybe it's a positive producer with a non-uniform field going away from it. Maybe it's a negative producer with a non-uniform field going towards it. The bottom line is the field lines are not parallel. It means the field changes depending upon where it is that you're trying to find the field strength. Now the bottom two equations we circled in another color because they're both valid when we have a uniform field. And when do we have a uniform field? We have a uniform field typically when we have two parallel plates. Now, yesterday I always drew, in all the diagrams that I drew with this, I drew the top plate as positive, the bottom plate as negative. There's no reason why it couldn't go the other way around. If we do the top plate negative and the bottom plate positive, the field lines this time would go upwards as opposed to downwards. But notice the field lines are parallel to each other. They're equidistant apart. That means that the field is a uniform field. It means that the field is the same no matter where it is in between those plates that you're trying to find the field. Also note that we draw this as two parallel metal plates. The bumper cars we used as the example of the real life situation where we see this. But there are other situations as well that aren't literally metal plates that approximate two metal plates over a narrower distance. For instance, here's the Earth. Here's a cloud. The bottom of the cloud becomes negatively charged as a result of friction. Well, that induces a temporary separation of charge in the Earth so that the top of the Earth is positively charged. Now, the Earth is curved. The cloud may be curved as well, but over a very small distance, over a very small area, it looks pretty much like these are parallel plates. So we would say in that case that we have pretty much a uniform electric field. Usually when we see a problem involving this, we're dealing with literally two metal plates, but not always. Okay, we could be dealing with something that's approximately two metal plates. That make sense? One final thing to note here, those are kind of slanted. Those should be straight up, right? You guys know that those should be straight up. The other thing that I want to point out is that we also get what's called edge effects here, and I didn't tell you about that yesterday. These edge effects are what happens at the edge of these parallel plates. So if you look at the outer edges of the parallel plates, we actually get a non-uniform field at the edges. And the reason is because the edges act more or less as point sources. They act more or less as, here's a charge, and the electric field goes like this between them. That's a non-uniform field, but you're never going to be asked to analyze, at least mathematically, the edge of this, or, for that matter, the edge of this. All right, let's take a look at the rest of this here, the rest of this little summary table. Do we use the first equation around a producer? Yes, a point source producer. It can be a positive producer, it can be a negative producer. Bottom line is it's a point source producer. It's going to look like this. It's going to look like this. Can you use the third one? Let's take a look at the third one. E is equal to delta V over delta D. Can we use that one around a point source producer? No. Can we use it around a producer? Well, not in the way we typically think of it as a producer, right? Because that point source is what we typically think of as a producer. But you could make an argument that these two parallel plates are producers. And if that's the case, then yeah, we'd say, yeah, it can be used around a producer. I'm going to put a little star by that, because those parallel plates could be considered to be producers, but I'm going to still leave the word no in there because I don't want you to start thinking, oh, I can use it around that point source. You're never going to be asked a question that says, can you use this equation around a producer? You're just going to have to know when you can use this equation and when you can't use this equation. So if what we've said there makes sense to you, it doesn't really matter what word we put in there, as long as you understand what I mean by no. I mean that you can't use it around something like this, but you can use it in between something like this. Finally, that middle equation that we call the universal equation, we're not going to use it around a producer when we have information about the producer. But I'm going to star that one as well, because you can use it with a producer. It's just that you have to have information about the experiencer. So maybe you got something like this, but you've got an experiencer somewhere in that field. Maybe you've got something like this. You've got an experiencer in that field. The bottom line is you're going to use it when you have an experiencer, something feeling the field. Can we use these equations when we're dealing with the electric field experienced by a charge? Well, no, this is the producer equation, right? Okay, this is nothing to do with the experiencer. Of course, this one I'm going to change actually. You can use this in the context of an experiencer, just the same as you can the first one in the context of an experiencer, but it's not for an experiencer. It's for a producer. So we're going to say no for this one, even though you can use it with the experiencer equation, but it's no different than the first one in that sense. Can we use the first one for parallel plates? No, of course not, because that's a uniform field between parallel plates, and the first one is for a non-uniform field. The last one, of course, that's what it's for, is parallel plates, or something that approximates parallel plates, like the example of the cloud on the ground that I just gave you. And finally, the middle one, yeah, you can use it between parallel plates, but only if you have an experiencer in between those plates. Rutger, you had a question there? Yep. Is that okay? Okay, remember this Venn diagram. Okay, honestly, that's what's helpful to me, is this Venn diagram. Okay, we don't have to start remembering an entire table. If we can visualize a diagram like this, we can figure out the table. We can figure out when each of them is allowed to be used if we can just remember that one little diagram there. All right, we had a couple of questions for homework here. Let's take a look at both of those here now, page 568. These are both pretty straightforward, actually, I think. Okay? Anybody have any issues with either of these? No? No, none? All right. Well, let's take a look at a multiple choice question then, if we don't need to go over one of these, because there's a good multiple choice question that goes along with this. It's multiple choice number 47 and numerical response number 48 that appear in your booklet. It goes with this information on this automotive wiring here. Now, I'm going to give you a little bit of background on this before you tackle these questions, okay? This question came from, I believe, 2001. That's 14 years ago. This question is 14 years old. That was a number of years before the curriculum shifted to not include certain things and to include other things. The curriculum then was different. It was similar to what it is now, but not quite the same as what it is now. One of the things that was required for you to know in 2001, but is not required for you to know now, is something called a transformer. This involves a transformer. Now, the reason that I've included this question now, even though transformers aren't required for us, is because although this makes use of a transformer, that's not what they're trying to ask here. They're trying to test something that we still need to know. But if you were to get a question now involving a transformer, they'd give you a little bit more background. Okay, it's entirely possible that you could get a question involving a transformer. That happens all the time. We get questions involving applications that we've never seen before. Even if we weren't doing this question, you could still get that. But they always explain it. Right? They always explain what it is that you're looking at if you've never seen it before. So if they were to give you this question now, they'd give you the information that's there, but they'd also tell you that the purpose of this transformer is to change the voltage from a low value of 12 volts to a high value over here of, maybe 100 volts, maybe 1,000 volts, maybe 20,000 volts. So you're changing the potential difference from 12 volts over here to 20,000 volts over here. They would also tell you that this is what we call the primary coil, and this is what they call the secondary coil. Again, prior to the curriculum change, you would be expected to know that. Now you wouldn't. But given the information that they've given you and that I've just added to this, this question becomes fair game for 2015, even though theoretically you would have never done transformers before. So take a read at that, guys. Add to it the information that I've added, and then take a look at the two questions, questions 47 and 48, that appear in your worksheet booklet. All right, everyone, let's have a look here now. 47 asks us for the strength of the electric field induced in the gap of the spark plugs. Well, the spark plugs are over here on the secondary side. On the secondary side, that means the potential difference in the spark plugs is 20,000 volts. In the distance, the gap, the distance between the electrodes of the spark plug is 2.00 millimeters. So we're going to say this is delta V, and we're going to say delta D, the distance between the plates, for lack of a better term here, is 2.00 times 10 to the minus 3 meters. It looks like to find the electric field there, we're going to say E is equal to delta V over delta D. Okay? Electric field between two parallel plates. 20,000 volts divided by 2 times 10 to the negative 3 meters gives me what? That's 2 times 10 to the 4, 1 times 10 to the 7, is that right? 1 times 10 to the 7. We could say volts per meter, or we could say newtons per coulomb. The answer for that one would be D. Now, some of you may be looking at that and saying, well, geez, like that's not parallel plates. That's more like here's an electrode, right? That's more like kind of 2-point sources, right? Almost. So we shouldn't be able to use that electric field between two parallel plates, right? Okay, remember what we have here. Okay, let's say if this is the negative one and this is the positive one, then we have an electric field that looks like this, right? These would be my edge effects. And you could say that in the middle, directly between them, it's a straight uniform field, directly between them. So we're approximating two charged metal parallel plates by these two electrodes. Yep. I'm sorry? Yeah. For an infinitely small region, for 2-point sources, yeah, you could say that. That's almost what we have there, right? All right, the second question says the acceleration of the electrons across the gap is what? Well, we have the electric field now. Its value is 1.0 times 10 to the 7 newtons per coulomb, or volts per meter, however you want to say it. And we know that the electron experiences that electric field, so let's set that equal to F over Q. But we're looking for the acceleration, not the force. Well, get the force first. Charge is going to be 1.6 times 10 to the minus 19. You take that up by multiplying. The force ends up being equal to, what is that, 1.6 times 10 to the negative 12 newtons. And then we're going to say A is equal to F over M. 1.6 times 10 to the negative 12 newtons divided by 9.11 times 10 to the minus 31 kilograms. And what does that work out to be when we do that math? Right? 1.8 times 10 to the 18 meters per second squared. Now, how do we express that? Hold on. We're looking for the values of A, B, C, and D. We'd express that on our numeric response answer sheet as 1.8. If it said not A decimal B, C times 10 to the D, but rather B times 10 to the W, your answer would be 1.8. Make sense? Okay, we want it this way, but it could very easily be asked this way as well. All right, your homework for the weekend, remember, is that which I assigned yesterday, worksheet number 8. Okay, let's get that done for Monday. That's it. Have a good weekend, everyone.